Alternating series remainder it's very straightforward. It's along the same lines as the approximation stuff we were talking about yesterday. It's basically the idea that once you know that a series converges on a particular value, then you would take steps to figure out what it converges to. Right? So then the question would become, is an approximation good enough? And in a lot of cases, it is. Right? As we learned yesterday with the approximation technique that we talked about involving the integral test. Right? So this is one that's specifically related to the alternating series, but it's kind of cool, and it also it's not difficult. Right? It requires some numerical computation, but nothing too earth-shattering. Suppose the series has terms that are alternating, decreasing in magnitude, having a limit of 0, aka a converging alternating series. If the series has a sum that we call S, then this would be the relationship that holds true. Right? But this is the important piece. You can approximate the sum by using the nth partial sum, and your error will be bounded by the first truncated term. All right? So what that means is that if I were to, for example, in the first problem, find the fourth partial sum, which would be S sub 4. Whatever the fifth value is, the fifth term of that sequence, that's going to be the amount of error that you could possibly have, the maximum error. All right. So it holds with the same idea as yesterday, where if you keep incorporating more terms, you're going to reduce the amount of error in your approximation. But here, you're actually, instead of having to use an integral to compute the amount of error, it's just going to be the next term in the sequence, right? Which is pretty easy to come by. Right? So the only issue is you have to actually come up with the sum of the first four terms, which is not terrible, but it's not always something you want to do. Right? So it's alternating, which means that we have to account for the fact that there's going to be a sign change. So if I plug in a 1, I'm going to be looking at a power of 1 minus 1, which is 0. So the first term is going to be positive. So negative 1 to the 0th power is positive 1. So 1 over 1 factorial. All right, the second term is going to be negative. All right, so that's going to be negative 1 over 2 factorial. Plus positive 1 over 3 factorial. Plus negative 1 over 4 factorial. All right, so we're finding the sum of the first four terms. So we'll have to crunch those numbers, but you know, that's not the end of the world. Now, the fifth term of the sequence, so the fifth term, so this is, I'll just make a little note, a sub 1, a sub 2, a sub 3, a sub 4. A sub 5 is going to be a positive 1 over 5 factorial. That's going to be the maximum error. All right. So this is going to be our approximation, S sub 4. And really, every partial sum is an approximation. It's just a question of how accurate it's going to be. If I were to say, all right, I'm going to approximate this series by just going out one term, you're like, okay, well, the sum is 1. All right, well, I'm going to be way off, but that's an approximate. All right? It's more like a shot in the dark, but it's still an approximation. So I just got to crunch these numbers. The recommendation is to, as you're dealing with more and more complicated situations, get the calculator involved. All right, so let me show you a little technique that I like to use. It's numerical in nature. It's a slight variation on what I showed you yesterday. Just pop it all in my calculator, or I'm never going to remember to do that on a test. Open notes test. Maybe you write down these steps in your notes. And when it comes to doing this, it's all there for you. I don't know. But you know what, like, I used to write down all the steps for my students and give like nice handouts and everything. And then I realized that people weren't paying attention during class. And so they were just waiting for me to hand them the handouts. And then I figured the added little bonus of that would be if I created a video where I was going through all the calculator processes, and that was the only way, like if you forgot to do how to do something on a calculator, the only way you can get the information would be to go to my YouTube channel and watch the video. Then I'd get more views. And then maybe you'd hit the like, thumbs up, and then I can benefit from it. They demonetized me, so I don't get any money. But now it's just a matter of pride. I didn't have enough views because I wasn't getting enough views. Yeah, I know, it's crazy. My biggest views are like whimsical topics where it's like, oh, let me just talk about this. And I'll get thousands of views for that. Or tech assignments. Tech assignments do well on YouTube, but like regular lessons, nah. Teach an Algebra 1 class at high school. I get one view for each one of those videos. I know exactly who it is. He's a really good looking guy who knows a lot of math. Yeah, it is me. It is me. Yeah, most people have the moment of like, all right, I'm not sure if he's talking about himself. He knows a lot of math. Yeah, possibly. Bad thing I got fixed. All right, so this one, I just crunched the numbers while we were talking. It's 1 over 120 slash, I've done that 1,000 times already, so I know from experience that it's 1 over 120. So what we get from this is the idea that the approximation, so first off, it has to converge. We have to know it converges on a particular number. Otherwise, what are we approximating? This is the approximate value, 5/8. And we will be off. If we are off, we're only going to be off by at most 1 over 120. Or 1/120th of a unit. All right, that's good. That's not bad at all. All right, so less than 1%. All right, what we wanted to do is have it be less than 1 over 100, so less than 1%. We achieved that because 1 over 120 is less than 1 over 100, so this is a good approximation. All right, now everything is based off of scale. So if you're talking about, I don't know, atomic mass, and I tell you that it's off by like 0.1 gram, that's probably not a good thing. Right? But if I tell you I'm talking about the weight of a car and it's off by 0.1 gram, then that's great. You know, if I'm approximating the weight of a car, I'm like, and I'm only off by 0.1 gram, I'm like, that's pretty solid. Like, some prior knowledge must have come into play there. All right, so it all has to do with context, but generally, the small, like if you get something less than 1%, you're in pretty good shape. So use the results to find an interval in which S must lie. So that's where we kind of generalize this. Let me do that in a different color. I'll do it in black. S minus S sub n. Now, n in this case is 4. Has to be less than a sub 5. All right, S minus S sub 4 has to be less than a sub 5 by rule. All right, S minus S sub n has to be less than a sub n plus 1, and we denoted all of this to amount to S sub n being S sub 4 and a sub n plus 1 being a sub 5. All right, what this means algebraically is that S minus s sub 4 is going to be between negative a sub 5 and positive a sub 5. Now, getting particular here, it tells me that negative 1 over 120 is going to be less than s minus 5/8, which in turn will be less than 1 over 120. So if I add 5/8 to everything, I'm going to get an interval that will capture the true sum. All right, so 5/8 minus 1/120th, and so math right now, and then so 37 over 60. And 19 over 30. Bless you. All right, so the true sum has to be in that interval. And really, if you think about it, we only had to go out 4 terms in order to get a good approximation. That's pretty good. All right, you may say, okay, well, let's see if we can do better. And by better, I don't mean more accurate. I mean less accurate with an acceptable amount of variation, acceptable amount of wiggle room, right? So if I, for example, only went out 3 terms, then I will have an amount of error consistent with 1 over 24. So 1 over 4 factorial amounts to 1 over 24. So 1/24th of a unit. So you're talking like close to 5%, roughly, 4 to 5%. So if you're willing to accept an amount of error in the interval of 4 to 5%, then you would only have to compute the sum of these 3 values. Right? So if you're looking for a ballpark figure, then that might not be bad. All right. Now 5/8, like if I were to take just the first 2 terms, 1 minus a half is a half. 5/8 is in the neighborhood of 1/2. 4 out of 8 would be 1/2. So you're looking at 1/8 in terms of the amount of variation. So is that 0.125? So 12.5%. So even just going the 2 steps, you're looking at only 12.5% of deviation. So even that, depending on the context, may not be terrible. Right? So it depends on the situation. But what this gets for us is the idea that once we have convergence, if an approximation's all you need, then there isn't really much you need to do. But if you have to come up with exactitude, then that could be a different story. All right. So I'll put a star on the next one, because it's really just the same kind of problem. Just you need to figure out how many steps you need to get in order to get an error that's less than 1 in 1,000. So that's not, in terms of increase in difficulty, it's marginal. All right, but on page 69, the question was for us to determine how many terms are needed to approximate the sum of the series below, so that the estimate differs from the actual sum by less than 1 in 1,000. Right, so 1/1000th of a unit. Justify your answer. So what we do is we just keep expanding until we get a term that has a value that's less than 1 over 1,000. Right? So we know it's going to be an alternating series. So if I plug in a 1 to start, that's going to give me an even power. Even power, so negative number to an even power gives me a positive. So 1, positive 1 over 1 to the 4th is just going to be a 1. Plus, the next one is going to be negative, because if I plug in a 2, it's going to give me an odd number on top. So a negative to an odd is going to give me a negative. So negative 1 over 2 to the 4th. We'll simplify in a sec. Plus, the next one is going to be, now that we know what the pattern is for the top, we know it's going to be positive, negative, positive, negative. So the next one's going to be 1 over 3 to the 4th. Now, as you go, you may want to simplify. So this would be 1 minus 1 over 16 plus 1 over 81 So the next one up would be plus a negative 1 over 4 to the fourth. So that would be minus 1 over 256, 16 squared, I think. Then the next one would be plus 1 over 5 to the fourth. So that's going to be 1 over 625. All right, 1 over 625 is not less than 1 over 1,000. We need to keep going until we get a term that has an absolute value that's less than 1 over 1,000. All right, so next up would be plus a negative 1 over 6 to the fourth. So minus 1 over, it's the same as 36 squared, which I'm pretty sure is 1296. And that is less than 1 in 1,000, all right? Because you're taking 1 and dividing it by a number that's bigger than 1,000, so its fractional value would be smaller than the fractional value of 1 over 1,000, all right? So this is our cutoff. So this would give me my approximation. 1, 2, 3, 4, 5 terms, so S sub 5. All right. How many terms are needed to approximate the sum of the series below? All right, 5 terms. They're not actually asking us to determine what the approximation would be, which wouldn't be too terrible because I just typed that in the calculator anyway. But it's saying just to determine how many terms are needed. So 5 terms are needed. And that's because the 6th term is less than 1 over 1,000. All right, it's magnitude anyway. All right, so it's within 1/1000th of a unit of the correct sum. I mean, that's not bad. Okay, so now again, if you needed to figure out this sum, I'll do it again on the calculator, just because it's a skill. 2 more messages. Hey. Then we get into absolute and conditional convergence. Still living with the alternating series. All right, so we'll be done with this in a minute. Absolutely convergent if the absolute value of the series is convergent. All right, so that's the absolute part of it. It's conditionally convergent if your alternating series converges, but the absolute value of the alternating series does not. All right, so it essentially means that you have to establish 2 things. One, whether or not your alternating series converges. So we get to work on that. So if you want to use the calculator to run the numbers, you can. Or you could just plug and chug. You know, in all honesty, in most cases, plugging and chugging is not the most challenging way to go. So a sub n here, we're looking at 1 over the square root of n. The expansion of that would be 1, then 1 over root 2, then 1 over root 3. We know it's alternating, so you could ditch that step because the negative 1 to the nth establishes that it's alternating. All right. Also, determine whether the given alternating series converges or diverges. So it's really kind of letting you off the hook with that. I just need to make sure that it's decreasing, and in this case it is. All right, decreasing. Now, if I was not sure that it was an alternating series, then I might want to show the positive negative, but even that's a stretch because once you see a -1 to a variable power, you know it's alternating. All right, so I need the limit as n approaches infinity of 1 over, I'm going to write it as n to the 1/2. All right, and so that's going to be equal to 0. So therefore, the series from n equals 1 to infinity of -1 to the nth times a sub n converges by the alternating series test. All right, so that's 2 pages ago. Same skill. Pretty much the same problem. But now what I want to do is establish whether it's absolutely convergent or conditionally convergent. And all that amounts to, and it's really, well, I'll say usually, I was going to say mostly, but it's usually a fairly easy process because what I'm going to do is I'm going to find the sum of the series without the -1 to the nth power there. All right, I'll show the intermediate step just for this one case because the sum from n equals 1 to infinity of the absolute value of -1 to the nth over the square root of n. Really, if you think about it, the absolute value is not going to impact the radical because n's got to be positive based on the bounds of the summation. So square root of positive is positive. -1 to the nth is going to be positive or negative depending on what n is. But if I'm telling you I'm taking the absolute value of it, then any negative is going to go to a positive. So really, anytime you're looking for the absolute value of an alternating series, all you're doing is dropping the -1 to the power part of it. All right. So what we get from this, 1 over n to the 1/2, is that that's going to converge or diverge? Converge, diverge, less than 1, yeah. Diverge by what test? By p-series test. And that's because the p-value is less than 1. All right, so more than 0, less than 1. Less than or equal to 1. All right, so therefore, lots of therefores in this one, that original series, -1 to the nth times a sub n, is conditionally convergent. Yeah, but it's the weird transition where first we're addressing the alternating series itself. So all of this stuff, let me just cordon this off a little bit. All of this is the first part. Because how could it be absolutely convergent or conditionally convergent in terms of an alternating series if it's not an alternating series that is convergent or divergent to begin with, right? So first you establish its alternating series, then get into the characteristics of an alternating series, then determine whether it converges or diverges. If it diverges, you're done, right? It's not going to be absolutely or conditionally convergent if it's a divergent series, right? So from a student standpoint, you're rooting for divergence because that means you get to stop here, all right? So once you establish that it does converge, then find the absolute value of your original series and determine whether that converges or diverges. whether it converges or diverges will dictate whether the original series is absolutely or conditionally convergent. All right, so if convergent and convergent, then it's absolute. If it's convergent but then divergent for the absolute value, then it's conditional. If it's divergent, or at least the original alternating series is divergent, then that's the end of it. No more work after that. Right. So the second example is very much like the first one. So I'll put a beefy star on that bad boy. Absolute versus conditional convergence. I mean, it really just boils down to the idea, again, that you're determining convergence twice. One for the alternating series, and then also for the absolute value of the alternating series. So my first move would be to determine whether it's a decreasing and alternating sequence. So just a few values, all you need. Starting with a 1, I get a positive number up top, so 1 over 3. Then we're going to have minus, you put a 2 in, it's going to be an odd exponent up top, so negative. So 1 over 3 squared is going to be 1/9, plus 1 over 3 cubed, which is going to be 27th, and so on. So it's alternating and decreasing. All right, so what I'm going to do is find the limit as n approaches infinity of 1 over 3 to the n. All right, which is going to be what? Say again?
Why not negative 1?
Oh, because when you're applying the alternating series test, you're taking everything except for the part that makes it alternate.
Okay.
All right. So this gives us a result of 0, which is what we're looking for. All right. So if you get 0, it means it converges by the alternating series test. If you get something other than 0, it means it diverges, but by the nth term test or the divergence test. All right. So that's the first part. So we know it converges. Now it's a question of will it do it absolutely or conditionally. So I'm going to take the absolute value. So n equals 1 to infinity of the absolute value of negative 1 to the n plus 1 over 3 to the nth, which is going to simplify very nicely, shockingly nicely, to 1 over 3 to the nth, which cleans up even further to 1/3 to the nth power. So this new series, we just ask ourselves, well, does that converge? And if so, using what test? So I'll give you the first part. It converges by exactamundo, geometric series test, and the condition that allows that to happen? Exactly. Absolute value of r is less than 1. All right, so the original series converged, the absolute value of the series converged. So this whole series, the original series, not the next generation, is absolutely convergent. So then we move on to the ratio test and the root test. And this is the last page we're going to do tonight. All right. So, ratio test, you can look at it and say, well, it's got ratio in it. So, series that's in the form of a ratio could be a ratio test situation. What you want to be looking for are ends that exist top and bottom, but are not nth rootable. All right. So if that's the case, then what you're looking at is possibly, but I'll even say most likely, a ratio test situation. Unless the exception being that you can simplify it in such a way that it ends up being a P series, not a P series, geometric series. All right. So you might look at something that's very elaborate, but then it cleans up nicely to something like 1/2 to the nth power. If that's the case, it's geometric series, right? If you see a factorial in it, it's going to be a ratio test situation, all right? It's almost assuming that there's an n top and bottom, and it's not alternating series. If you see a factorial in it, it's almost always going to be a ratio test. Okay? So the question becomes, well, what do we do? Well, the process tells you what to do. We have to find a sub n plus 1. A sub n is given to us. We have to determine what a sub n plus 1 is and then find the ratio of a sub n plus 1 and a sub n, which requires algebra. Once we do that, we find the limit of that absolute value. If it ends up being less than 1, it converges. The original series converges. If it's more than 1, it diverges. All right, so let me make a note. This is my a sub n. A sub n plus 1 is just the next term in the series, really. So I'm just replacing all my n's with n plus 1s. So 2 to the n plus 1 over n plus 1 factorial. All right. Now, recommendation, simplify this or clean it up algebraically now, and then create your ratio. So, what do I mean by that? You have a sum in an exponent. Sum could be broken up as a product of two exponentials. So, instead of writing 2 to the n plus 1, I'm going to break that up into 2 to the nth times 2 to the first, or just 2. All right. Again, the idea is to simplify it. So when I create the ratio, I'm going to want some things to cancel. One of the things I'm going to want to cancel is the 2 to the nth. And so by breaking that up, I'm going to make that happen. All right. There's other ways to do it, but this is the most efficient way. All right. N plus 1 factorial can also be thought of as n plus 1 times n factorial. All right. Because every number factorial is the product of itself and the next number down the line factorial. So like 5 factorial is 5 times 4 factorial. 10 factorial could be thought of as 10 times 9 factorial. N factorial could be thought of as n times n minus 1 factorial. Here, n plus 1, the next number below it would be n factorial. All right, so I'm going to create my ratio in limit form. Two to the nth times 2 over n plus 1 times n factorial all over 2 to the nth, let me make that look more like a power, 2 to the nth over n factorial. And if your reaction is, how the hell am I supposed to find the limit of this? It's a mess. Well, you just answered it. It's a mess. Let's make it not a mess. 2 to the nth is going to cancel. N factorial is going to cancel. Basically, everything that made this limit difficult cancels. right on down to 2 over n plus 1. This is all that complex fraction stuff you did in college algebra or algebra 2. Fraction over a fraction. If you have a common factor between the numerators, you can cancel them. Common factor between the denominators, you can cancel them. It's what you would get if you did the keep change flip and then did the canceling, but you're saving yourself a step. Right. So now I have a much simpler ratio. Much simpler. That absolute value is there, kind of annoying, but we know that functions transcend limits. So I can take the absolute value out and make it the limit as n approaches infinity of 2 over n plus 1. What is the limit as n approaches infinity of 2 over n plus 1? 0. And the absolute value of 0 is indeed equal to 0. All right. So I remember when I learned all this stuff, it was a question of, okay, sometimes 0 is a good number, sometimes it's a bad number. When is it good? When is it bad? I don't know. Hopefully the test is open notes. All right, cool, it is. Right? If your limit is less than 1. Doesn't matter what it is, as long as it's less than 1, then your series converges. All right, so undo. I don't know why that happened. So therefore, the sum from n equals 1 to infinity of a sub n converges by the ratio test. You have to write it out. The limit is less than 1. All right. This RT could be something else. So this is what I was talking about, I think, yesterday when I was talking about abbreviations the first time. That there are exceptions. All right, so. But ratio is not a lengthy word, so I think we'll all get over it very quickly. Right, so it's really this part of it that makes it complicated. If you can get this part of it, then you're good, because everything else cleans up nicely. So I'm going to put a star on the second one and then move to the third one. Yeah, the third one. Yeah. All right, so we have our a sub n. We need a sub n plus 1. All right, so all you're doing is you're increasing your n value by 1. Right? You could think of it as replacing every n with an n plus 1, but that just amounts to increasing n by 1. So if I were to change this by increasing it by 1, it'd become n plus 2. So n plus 2 factorial. Over 3 to the n plus 1, I almost said factorial. 3 to the n plus 1 only. All right. Now, in the process of simplifying, we hope to be able to cancel some of this stuff out. The hope specifically is that you'll cancel out pretty much all of a sub n. All right, that's what happened in the last problem that we did. Maybe you'll have a constant multiple laying around, but that's all right. Now you want to cancel out the beefy parts of it. So if that's going to happen, I want to break this up to n plus 2 multiplied by the number that's 1 less than it factorial. What's a number that's 1 less than n plus 2? N plus 1. For the exponentials, you're basically undoing keep the base out of the exponents. So 3 to the nth times 3 to the first. All right, so then all we're doing is we're finding the ratio, the limit of the ratio. So limit as n approaches infinity of the ratio. And one thing you can do if you want, I mean, not everybody wants to do this, but I'll give you the opportunity to do it. You do the cancellations on the fly. You know, if you know what part of this is going to cancel out with what part of that, then you could just go right to the simplified expression without showing all the details. Not everybody wants to do that, so I understand. So n plus 2 times n plus 1 factorial over 3 to the nth times 3 over n plus 1 factorial 3 to the nth. Cancel all that is cancelable, which should be a fair amount of it. And again, with the idea being that if you're doing it right, damn near all of a sub n should cancel out. The only thing, again, you might be off by is a constant multiple. All right, so you're left with n plus 2 over 3. All right, which amounts to the same thing as the absolute value of the limit as n approaches infinity of n plus 2 over 3, which is the absolute value of what? Infinity. Absolute value of infinity is infinity. And so we now know that this series diverges. Let me actually state what the series is. Another ratio test. And that's because the limit is greater than 1. Now, it doesn't have to be specifically infinity. It just worked out in this case. It just needs to be greater than 1 to diverge. Less than 1 converges, greater than 1 diverges. So that's the ratio test. And again, the hardest part about that one is the algebra. I found, just through personal experience, that people who struggle with this one, they don't know what to do with the factorials. So if you can study that part of it, then everything else is going to work itself out, because the parts with the exponentials, people intuitively have a good sense for. It's just the factorials tend to throw people off. All right, and I've seen everything from like canceling an n plus 2 factorial with an n plus 1 factorial, like just trying to cancel it out to like a 2. I've seen that. I've seen attempts to expand it, like actually expand it all the way and come up with these like monstrous expressions and try to cancel it out that way. It's just a nightmare. Just take some time and try to understand why we're able to do things like this. And honestly, it starts with numerical examples. If you can do that, then it goes a long way. The root test is much easier, which is why I don't feel bad about throwing it on at the end here. Usually applies when the variable power in the numerator and denominator, but also it has to be nth rootable. All right. So you're not going to see cases where there's a factorial involved, because you can't easily take the nth root of something that is in factorial form. Right? There are exceptions to everything, but generally what would have to happen is you'd have to have an nth power both top and bottom of a fraction, or it would have to simplify in such a way that an nth power would emerge in the top and bottom of a fraction. If that happens, it's very simple. What you're going to do is take the nth root, the absolute value, and then find the limit. All right, so first we identify the a sub n. The absolute value of a sub n in limit form. Now, just a quick aside here. The nth root, yeah, that's a nice way of writing it. It's concise, it's good looking, I guess. Great way to stay in shape. But you're better off writing it like this. A sub n to the 1 over n power. That's going to do a lot more for you, I think. So we're looking at e to the 2n over n to the n, raised to the 1/nth power. One of the properties of exponents tells us that if you have a power multiply or power to a power, you're going to multiply the powers. All right, so this ends up being e to the second over n. All right, 2n times 1 over n is going to go to 2, and n times 1 over n is going to go to 1. All right, this is the same as saying the absolute value of the limit as n approaches infinity of e squared over n, which is the absolute value of what? 0. Yeah, e squared is a constant. So constant over infinity is going to go to 0. So this is going to end up amounting to equal 0. And one thing that's consistent between the ratio test and the root test is really the conditions. If your limit is less than 1, it's going to converge just like the ratio test, and if it's more than 1, it's going to diverge just like the ratio test. So therefore, converges by the root test and again that's because the limit is less than 1. Alright, and so as you suspected, I'm going to pop a star on the second one. Second one's actually easier. I don't know if anybody claimed, honestly I can't remember if anybody claimed this typo, but that spacing just bothers me. So submit it. If somebody already has it, then you're out of luck, but you never know. Right? But if you see it anywhere else, that absurd spacing, that's a typo. But as long as you have a general idea what the process is, it's not going to be too much trouble. It's just, something like number B. Something like one of my teachers. I don't think they ever said it the right way. It was always letter 2 or number B. And just, I'm becoming my father. So, B, part B here, is probably a little on the easy side. And so you look at it and say, well, it looks like it's not easy. But in any case that doesn't involve the factorials, they actually clean up pretty nicely. All right. So we have n plus 1 squared times 3 to the n plus 2 over 2 to the n plus 1. All right. So we're increasing every n value by 1. I mean, that's all this is really telling us. So replace an n with an n plus 1, replace this n with an n plus 1, but really you could even think of it as, I'll take an n plus 1 and replace it with an n plus 2. If I had an n plus 5, I'll replace it with an n plus 6. All right? So it's just really a question of, okay, now that I have this, what am I going to do with it? All right? So that's where the magic really happens. But it's not really black magic. It's more like the fun, fantastical magic. Like the first half of a Harry Potter movie, you know, before it starts getting serious, because they always followed the same formula. It was like whimsical, let's learn a new spell, and then all of a sudden, here's Voldemort, he's trying to kill him. Now what are we gonna do? Use that spell you learned earlier. All right, so it's the same idea here. This is like the whimsical kind of magic. All right, so it all comes down to stuff like that. Break that up and see where it gets you. Okay, and while we're at it, we got another one right here. We'll break that one up too. Anytime you see a summer difference in an exponent, just break it up. All right, so I'm looking at n plus 1 squared times 3 to the nth times 3 squared. I'll write it as 3 squared, but you could write it as 9, obviously. 2 to the nth times 2 to the first, or just 2. All right. So we'll create the limit, which is going to consist of the ratio of this juicy expression here and this one. All right, so we'll do that. I'll go purple for those keeping score at home. On the fly here, I'm gonna break this up. So we'll have n squared times 3 to the nth times 3 to the first, or just 3, over 2 to the nth. Whoa, look at that. It's just really surprising to think that this is gonna clean up beautifully. Like, stunningly beautifully. Because pretty much everything that's difficult about it is going to cancel away. We got some constants left over. Can live with that. Limit as n approaches infinity. I have now. I mean, I guess. Oh yeah, I forgot. Honestly, whoop. Surprising that I forgot that. Because it was there the whole time. 3 goes into 3 squared 3 times, right?
Get the n squared, can you get rid of the n squared at the bottom? Because if you distribute the exponent between n plus 1, wouldn't that just cancel that out?
Unfortunately, not directly, because that n squared is going to be connected with an addition. And so you can't break up addition with a division.
All right.
But we will be able to get rid of it in a more definitive way in a sec. So we're looking at, when we keep change flip all this, 3 times n plus 1, the quantity squared, over 2n squared. And at this point, you can kind of, it's up to you. You can go right to the final answer. If you're doing it in a calculator, definitely. Even if you're doing it by hand, still. Because you could reason it out that if I distribute this out, I'm going to get an n squared plus blah, blah, blah. When I multiply it by a 3, I'm going to get a 3n squared plus blah, blah, blah. All right? So you can even do that. This will become 3n squared plus blah, blah, and 1 additional blah. Okay. The reason why that's the case is because, or at least why we could jump right to the answer, is because when the powers are the same, all we're doing is taking the ratio of the leading coefficients. All right. So this is going to limit down to just 3 halves. And the absolute value of 3 halves is 3 halves. If you want, distribute the whole thing out. Make yourself comfortable, you know, with the idea that you didn't just box it up. You know, while you're at it, put it in a calculator too. Make triple short. But it's going to be 3 halves no matter how you slice it. right? And so this series diverges by the ratio test, and that's because the limit's more than 1. All right, so if it's less than 1, it converges. If it's more than 1, it diverges. And again, that more than anything speaks to why it's open notes. Like just thinking back to the last test that we did, like the alternating series. Okay, so if it's equal to 0, it converges by the alternating series test, but if it's not, it diverges by the nth term test. I'm never going to remember that. Well, that's okay, because you'll have it in your notes. All right. I kind of go back and forth on what my favorite test is. Sometimes I decide that this is my favorite just because it's the easiest one to recognize. And sometimes easy to do and easy to recognize are two different things. Because like I know that I can perform the geometric series test very, very easily. Sometimes I can't recognize something as a geometric series though. And if that's the case, it's great that I can actually perform the test, but if I don't know it's appropriate when to use that test, it's all over. All right? So sometimes you'll like sacrifice, an easy problem for one that you actually recognize. This is one of those. If it's raised, if both parts are raised to the nth power, it's screaming root test. And the idea is that you're going to take the nth root, right, and find the limit of that as n approaches infinity. So limit as n approaches infinity. And so again, here's my a sub n. 3n plus 4 over 2n to the nth. But then we're going to raise that to the 1 over n power, because the nth root and raising to the 1 over n, that's the same thing. So we get 3n plus 4 over n. 2n. You don't really need the absolutes here, only because, and in a lot of cases you really don't need them, just because your domain is the set of positive integers, and you have the sum of positive values and a product of positive values. So it's going to be positive no matter how you slice it. The only time you really need to have it is when there's negatives involved, right? But this is the same, and you don't really have to show this step either. You could jump right to the answer, because I'm looking at every one of these problems as a problem that you could potentially be doing in your calculator and not by hand. So all these steps that I'm showing, they're just to really expose you to the proper way of finding a limit, but with the idea that that's the fun exploration that we do in class. But when push comes to shove on a test, if you're in a jam, put it in your calculator. That's really all there is to it. All right. So coincidentally, this is also 3/2. So the absolute value of 3/2. Powers are the same, so I'm looking at the ratio of the leading coefficients. And so we're looking at 3/2. And so therefore, the sum from 1 to infinity of a sub n diverges by the root test, specifically because the limit that we just got is more than 1. So more than one, non-existent, anything, if it's less than one, you're good. If it's more than one or non-existent, then you would say it diverges.